Hello, everyone. Welcome to our April COSINC monthly webinar. We're hoping to continue this as a series every month. Pick a topic and go from there. If there's things you think you'd like to be covered, then let us know. But we should be publishing our schedule sometime soon. So today, I wanted to introduce X-ray computed tomography. So we have this tool. It's not technically part of COSINC, but I still help manage it over on main campus. And I tend to find it's a pretty new technique, so people aren't quite sure what it does. So I wanted to keep this presentation just as an introduction and an overview of what it's capable of. So I thought, before I started trying to explain how it works, jump straight into the results you can get out of it. So I like this example on the far left because we all know what a glass vial looks like. You know, it has a plastic lid, it has a glass container, and then inside the lid, there's maybe some sort of filter or seal. So you can see that here. Let me change to the laser pointer. So this is a glass jar that I imaged in our X-ray CT scanner. So you can see we've got the full jar here, but then what we can do is the full 3D internal image. So digitally, after I've taken the image, I can slice everything in half, and then we can see the little insert inside the lid here is revealed. And because it was a different density polymer, I think some sort of membrane here that helps with sealing, I could actually segment that out as a different material. And then a lot of CT imaging software is really geared towards quantification. So what I did was I measured the thickness of the glass wall around this section here. So this color scale here actually relates to a thickness over here. So we can see this side of the glass jar is slightly thicker at around 955 microns compared to the other side of the glass jar at around 898 microns. So I like this example because something we're all familiar with, and gets you an idea of how you can really see through things and cut through things digitally and quantify them too. This one's nice. This is some balsa wood that people were working on here from Will Srubar's research group. And then we managed to quantify and segment out these cell walls using some deep learning segmentation, because it's a difficult segmentation task. This was a metal filter, a metal mesh that someone wanted to quantify the porosity and the tortuosity. So the gray part here is just a digitally cut out portion of this metal filter, and the purple is the pore space. And then this sort of network here is a modeling of that pore space. Okay, so with that out the way, how do we make it work? So in our system, at least, we've got an X-ray source to one side. The sample sits in the middle, and the X-rays pass through that sample, and the X-rays are attenuated by the sample, and then that's detected on the detector. So we have a few different lenses here on our Zeiss X-Radia CT scanner. We can go all the way from, whoops. So we can fit in sample sizes. We've had, for example, like honeycombs all the way up to say 30 centimeters in height and width. They'll go into the sample, but we can only view say 5 centimeters of that at a time. We can do wide stitches and things, but 5 centimeters is a good ballpark for how large something can go. And then we can image something all the way down to half a nanometer voxels on the scale of, say, like a 500 nanometer field of view. And you need at least 5 voxels to image and quantify something. So think of a feature you could see is on the scale of 3 microns for an ideal sample. So in X-ray CT in general, you can fit an entire engine block into some tools, or we can go all the way down to millimeter scale fields of view. down to tens of nanometers. That NREL actually has the high resolution X-ray CT from Zeiss that can go down to that kind of resolution, which we can't quite reach. So as I said, we can get to, so think of your field of view is going to be a cylinder. And that cylinder max is going to be 5 centimeters wide and 5 centimeters tall, all the way down to 500 microns wide and 500 microns tall. And a good thing to keep in mind when you're planning your imaging is 1,000 to 1 voxel to field of view ratio. So let's say you want to see pores that are on the scale of 5 micron. Then you're going to need, then you're going to need, 5 pixels to see those 5 micron pores. You need 1 micron voxels. So you'll be able to image at that resolution over, say, a field of view around 1 millimeter. So it'll be very difficult if you have, say, like a really large part, 10 centimeter device, and you want to quantify all of the 5 micron pores within that entire 10 centimeter part. That would require such a huge image file size that would make it really impossible. And then one of the tricky parts about getting down to our low, say, 500 nanometer voxel size is the sample size. If your sample's too large, then the source and detector need to be further away, which greatly reduces the X-ray intensity. If your sample's larger, it'll also attenuate more of the signal. So we might actually completely run out of X-ray signal at the detector. So the signal to noise ratio will be really bad. And then the further the source gets away from the detector, we get some artifacts like penumbral blurring that will reduce that resolution. So, on paper, you'll have, say, a 500 nanometer voxel, but in reality, the limitations of the device won't allow you to really truly see that 500 nanometer voxel. And then the time frame for these images, like a single image, which is a full 3D reconstruction, is on the scale of tens of minutes for a nice large field of view, to for a tricky sample that maybe is highly attenuating, or a really small sample, or a really high resolution image, can take hours. We've had scans up to 10 or 12 hours, but typically on the 1 hour kind of scale is where we work. So practically, how does it work? Let's see if this video will play. There we go. Right, so here is an image I've taken of a bottle of Tylenol pills. So the Tylenol bottle is mounted in the middle of the X-ray CT, and it's rotated through 360 degrees, and a certain number of projections or 2D images are taken through that full 3D 360 degree rotation. And then part of the next step is really interesting. So let's say we're trying to image this 3D image of a pi symbol. And then what we've done here is we've laid it down flat and exposed it to the X-rays with a detector on one side. And we're going to rotate that through 360 degrees through this axis and take images the whole way around. So the tricky part about explaining this is we're going to sort of flip axes a few times, but think about on the next slide, just one single pixel slice through this axis of this 3D pi object. And then what we're going to describe on the next slide would happen for every single one of these single pixel slices through this item. Okay. So in order to reconstruct, basically turn, we have, say, 1,000 of these 2D images through the full 360 rotation of the sample. So that's what's represented by this video here. So each of those projections through each angle can be represented by its radon transform. So this is the data we actually get. We have an intensity value, which is here it's changing. There's this pi symbol for example has a constant density. So the only thing that's causing this signal to change is the thickness or distance traveled through the sample. Oops. Yeah. So this is the actual information that we're collecting. What we want to know is the back projection of that data. So we can do a reverse radon transform to get that image. You can see it was kind of blurry. So an extra high pass filter is added, which adds its own artifacts, but it looks much better than the original blurry image. So now what we have is this single slice here in essentially this 3D axis. So now we take each of these slices, reconstruct them all the way through, and we have a full 3D stack of images. So an important consideration when you are taking your X-ray images is how to get contrast, or how to see the different components of a material. So X-rays are attenuated by materials in a few different mechanisms, but mostly what we're worried about here is the total attenuation of each item. And then different energies are attenuated different amounts by different materials. So for example, our X-ray CT here in the lab goes from 30 kilovolts all the way up to 160 kilovolts. And then in this example on the right, you can see we have a few different materials. So I think I've messed up this graph somehow, but basically what we need is a contrast between these values to be able to see the difference between them. And typically, I think because I've gotten these numbers from NIST, something might be a bit too theoretical and not quite accurate, but typically the higher in photon energy you go, the less contrast you have. You can see quite clearly for the iron versus, say, soft tissue. The higher we go in energy, the less contrast we have, which might make it difficult to see the difference between the two materials. But for example, for soft tissue and air, yeah, I've plotted this a bit wrong actually. So this should sort of show a less contrast up here. So if we did want to see the contrast between soft tissue and air, we would need to run at a lower kilovolts. But in that case, if we also had iron present in our sample, the attenuation by that iron might be so high that we wouldn't get any signal through at all. So these are one of the trade-offs you have to make while imaging. You want the maximum possible amount of contrast, but you also need enough signal through that your signal to noise ratio isn't too bad. You can add contrasting agents. That's why iodine is included in here. So you can see it's quite a strong absorber. Typically, it won't absorb as much as iron because that concentration is, you're working with 100% iodine, which is represented here. But it's a great contrast agent for this reason. Okay. So there's a number of artifacts that can appear in the X-ray CT, but one that I want to describe and one that will typically ruin your day is something called beam hardening. So this is caused because in our laboratory CT, we're picking a particular energy to run at when we're using it. But what we actually get is the peak energy of the X-rays we produce will be what you set it to. But the actual spectrum will really peak in photon numbers, say about halfway down from what you've selected. And then because of the combination of different materials absorb different energy X-rays, so different amounts, combined with we have different a range of X-ray energies, causes this beam hardening artifact to appear. Because we're assuming at the detector linear Beer's law relationship for the attenuation. So we can't predict when, say, for example, the iron in the material is absorbing all of this low energy, but some of this, and then something like tissue would absorb some of this and none of this. So these differences in attenuation mean that we can't directly convert the signal we're getting here purely to attenuation values. So there are some things you can do to try and correct it. But for example, you can see all these sort of streaks coming out of this bright iron material here. So if you did have, I don't know why you would have tissue mixed in with an automated casting, but for example, we have imaged stents in the past, like a metal stent where you're trying to image the tissue surrounding it. And the beam hardening artifacts coming out so strongly from that metal stent are brighter than the tissue itself. So you can't see the tissue. So it's very difficult to image materials of drastically different densities. Okay, so onto some applications. We talked a bit at the start about this glass jar inspection. I like this example because, yeah, we all know what a glass jar looks like, and there's some really obvious quantification that goes along with it. Here's another one where it's kind of hard to tell from this image what we're looking at, but we have a stack of 1, 2, 3, 4 membranes. And then from this angle here, you can also kind of make out there's some fouling on the membrane. See these bright materials here, there's salts that have precipitated onto the membranes after them being used for some amount of time. You can see there's some less salt on this membrane. So I guess to describe it a bit more clearly, so this layer is air. This is the backing layer of the membrane. This is the fine surface of the membrane. Here's some fouling salts on the membrane, some more air, next membrane, and so forth. So because the salt is so much more dense than the air or the membrane, we could actually segment that out quite simply with a simple thresholding segmentation because it's so much brighter than the other materials. And then we could quantify the volume of salt on the surface of each membrane. X-ray CT is really great for, so obviously these are complete frogs and they had skin and flesh on them, so seeing the bones themselves is obviously quite useful. But apart from that, you know, even just taking an image sometimes is a lot more of an art than you would hope. So what you can do is you can image something in X-ray CT, and then you have a full 3D manipulatable digital image that you can angle and rotate and set the lighting exactly how you want it to for publication. And then in this case, these frogs had some sort of mutation that we wanted to label. So we could highlight specific mutations or problem areas of that animal and set them to certain colors to really highlight what we're trying to show. Here's another example of quantification, and this is really pushing the resolution of X-ray CT. So these pores here, I haven't got a scale bar here, apologies, but these pores here on the scale of say 5 to 10 microns. And these are the tiny little pores inside of mouse bones. So these individual mouse bones were imaged with our 20x objective all the way down to, I think it's a 600 nanometer voxel size. But you can see the wealth of information. So this one small portion of mouse bone has all of these little particles you can see here. They're all the pores or these lacunae inside this portion of mouse bone. So the wealth of quantifiable data you can get from CT is quite rich. And the analysis software that we use ORS Dragonfly, there's a number of packages available, but they're all geared to this kind of quantification and data analysis. Here's another example that Tomoko and I did actually for a webinar a couple of years back. So we wanted to show how the X-ray CT could be used to, say, give an overview of something like a mask here. So this is a portion of a KN95 mask, which of course we're often very familiar with a couple of years ago during the pandemic. And we wanted to, start with X-ray CT to have a quick look at the layers and determine which layers were the active layers, the finest fibers, and then we could take that layer into the SEM and get some even higher resolution images. So I guess that's an example of where in the SEM you might be hunting around for a long time, or it's difficult to get kind of an overview. This allowed us to locate the exact part of a material that we wanted to analyze in more detail with the SEM. So another thing you can do with the X-ray CT is you can take a zoomed out image. Let's see, what's the scale of this one? It's in the scale of like 0.5 centimeter or so. But then you can open up this image in Dragonfly ORS, pick a field of view that you'd like to zoom in on. In this case, it was this section here with the finest fibers, and send those coordinates back to the tool and get the exact area that you're hoping to see. I mean, that's definitely one of the drawbacks for CT versus SEM. You know, in the SEM, your images are immediate and you know kind of what you're looking at. Whereas with the CT, you put it in, you run it for an hour, and then you hope that you pick the right field of view. So this is one example of where you can really get the exact field of view you're interested in with a quick overview image followed by a slow high resolution scan. So I think it's pretty important to talk about segmentation and image analysis when we talk about CT, because typically when I train people, this is also an equal amount of training in addition to the imaging and the practicalities of that. It's how to get the most out of your images and manipulate them and get what you're trying to get. Right. So I guess the goal here, you know, this is this toothpick mount that I created, and this is the portion of that mask wrapped over it. So the goal here was to separate the toothpick from mask fibers. So how do you get from here to here? So typically what you aim for is that there's some sort of grayscale difference that you can simply separate. And there's algorithms to do that for you. There's a really famous one called the Otsu method. And what the Otsu method does is pick the position of the greatest interclass variance of your histogram and split that histogram into two. So in this case, if this toothpick was a little more dense and we'll say brighter or darker than the fibers, that would have worked really well. But you can see it's pretty similar in grayscale. So we couldn't do an Otsu split to segment out the toothpick from the fibers. So what we can do is train deep learning segmentation to separate out the two. So I think for this example, what I did was within the Dragonfly software, I might have spent about 10 or 15 minutes manually painting a couple of specific frames that represented the overall structure of the entire image. So all this pink here, I would have manually gone through, not really manually. There's still like what could have done something called like a local Otsu separation, where I just drew the painted the fibers, which would be easily to separate from air using some tools. And then I might have just manually painted the toothpick, the wood here. So I would have trained it a couple of layers, hit run on the train, and then that could have applied this deep learning model to the entire image through all the layers, and then the entire image would be segmented into fibers versus toothpick. So that covers the pretty quick intro for X-ray CT. I really just wanted to give an idea of how it works and the results you can get out of it, and hopefully inspire you for what it can do for your samples. Does anybody have any questions?
Okay, let me start asking you some questions. I'm new to this field, so I feel more confused than okay. So do people typically do large area scan with a lower resolution first and going back to the particular area to do more smaller pixel size? More like
no one
it's
really,
not, no, okay.
yeah, no one really does that. I mean, I do it quite often because I know how to do it, but you know, it's one of these things where you have to learn how to do it before you can really feel comfortable. I tend to use it a lot, but often you can work out what you want to look at without having to do this double zoom. But in this case, the tricky part was, let's see how to describe it better. So if we go back here, we're looking at, this is what you'll see when you're setting up the scan. You'll see this 2D image, and then you might rotate it to 0 and 90 degrees, make sure everything fits in the field of view you're hoping to see.
But you don't know it. You don't know what you will see until you do the data processing.
Exactly, yes. Yeah. So for something like in this field of view, it's okay. But then if let's say you zoomed into 20x, it really is, you can't see anything. You don't know what you're looking at because there's everything in front and behind it that you're looking at. So yeah, if you do want to zoom in on something, you'll need to use that method. But people don't use it that much. People often come with their samples ready where it's sort of obvious where the area of interest is. So it's not used that often.
Yeah, okay. So you kind of need to guess which parameters are good for that particular sample. And I see the question in the chat there. Let me see if I can read it. Is it possible to use XCT to differentiate segment materials, minerals based on density differences? Does this require calibration based on the phases that one can expect, say, in a complex rock matrix? I think it's a rock sample with a different density. Can you differentiate?
Yep. So as long as the density is, I don't have exact numbers on what densities we can differentiate, but if often in these rock samples, we can see lots of different densities and different grayscales. So it's usually a pretty good example of things that we can segment relatively easily. But as you ask, Srishti, about the calibration, so the tricky part is you kind of have to know what you're looking at. We could do, say, like a known sample at the same X-ray voltage, and so that you could compare grayscales. The difficulty is because of our because of these issues like different energies absorbing differently, and then also we have a bunch of different energies coming through, we can't always precisely calibrate the tool. So you would need to come with a lot of knowledge about your sample. It's not like EDS where we can put it in, I don't know what elements are there, and it'll tell us. We really need to know what we have and then use some good assumptions to back translate from a grayscale to exactly what phase or mineral is this.
Yeah, because absorbance is not, yeah. Okay, and let me see. I can read. Okay.
Run workshops. Not really, but as part of the training, I do show people how to work with X-ray CT data. I get the impression maybe you're working with geology samples. So there is, there's an upcoming session run by University of Texas in Austin, specifically training users how to work with geological samples. I think it might be coming in a few weeks actually, and they're putting out calls for, they provide the funding to travel there and get the training and everything. So if that fits you think, email me and I'll pass on the details for you. No worries. If you can't chat, it's okay. But yeah, email me for some more details about that UTCT course.
Okay, so if you have enough density difference, the should appear as contrast difference. You can differentiate, but you don't have a point, okay, 10, okay, this is called SiO2 versus something else, just from CT. So you have to study with different, you need to have a complementary data to kind of start identifying.
Yeah.
But
And Ginger Ferguson's group has done a little bit of calibrating, like to something called a Hounsfeld unit, which is sort of bone versus water. And that can help calculate like the density of the bone. Forget the amount of error in that image because of these issues like beam hardening in our laboratory polychromatic X-ray source. But it's definitely something you could try. The error bar is relatively large, but if you did want to calibrate, so I remember someone was trying to calibrate something like a bromine concentration for the conversion of their 3D printed photo reaction. And they got pretty close, but I think we could get there.
yeah, as usual, we have to have not only from one kind of data, we need to have a few different kind of data to support each other, I guess. Have you ever done in the geological samples, the XCT analysis of geological samples?
Yeah, we've done lots of them.
Lots of them. So sample is like a chunk or thin, I mean the thin sections for
yeah, people come with all sorts of things. They might come with just like a chunk of rock and pop that in. Someone came with a meteorite that was just too big for us. It was a 2-inch cube of solid nickel and iron, and it was just out of the range of our CT. So we sent their samples to Texas instead. And then we've had also geological samples. I think it's Connor who just left the call, where they've got really small, I'm going to say on the scale of like 100 micron zirconia particles that they would image. And then there's even a specific segmentation tool that's free called Blob 3D. I think it might be by the University of Texas people as well. And they can use that software to get all the specific metrics for those kind of samples.
So it's the XCT can be used with thin sections as well.
Yeah, you could use thin sections too. Well, unless it was so thin that it was below the micron resolution.
Thin section, but in the geology world, it's not very thin to me. So I think it's it's not nanometers. So
no, yeah, as long as it was, at least 10, 20 microns, you could see something.
For thin sections, do you need to rotate or you don't need to rotate? Just straight.
Yeah, they need to go through that full 360 degrees.
You have to go 360 on the thin sections as well?
Yeah.
Okay. Oh, if someone wants to get that 3D reconstruction, yes, you still need to rotate.
Oh, that's a good point. We do every now and then just do 2D images. So, we've had commercial clients come in with parts that they're worried about. Maybe from their shop, there's been some iron filings make their way internally. So, a few 2D images at a few different axes will show that. And then, if you did have a thin section, geological sample, maybe the 2D info would be enough for you.
Right, and I feel like if you have a lighter density, less absorbing material, but you have a much more distance X-ray can travel, absorbance is much larger, right?
Yeah, so that's a tricky part. If it was a pore or something, you wouldn't, it might be tricky. But yeah, if you were just looking, maybe if you knew exactly what was in there, but you just wanted to map it out, or maybe see roughly an area, you could probably do that in 2D if the matrix isn't too complicated.
Yeah, and since you are rotating, you have to align the rotation axis to a certain orientation, or it's not that sensitive?
Yep. Yeah, so you need to, typically you can just align something at 0 and 90 degrees, and it'll be pretty well centered. Sometimes you might put a frog in, and then that frog has some limbs sticking out at some weird angle. So then you need to check it every like 10 or 20 degrees or so to make sure that limb isn't sticking out out of the field of view at some angle. But most things you can just 0 and 90 center it, and you're good to go.
Oh, okay. So you get 2 points, then it's okay. Okay.
Yep.
Okay. And how long does training usually take?
I typically do 2-hour sessions. Because the image analysis is so daunting. Even just like, opening the files and looking at them and changing the window leveling and things like that is painful to learn on your own. So I tend to include some image analysis as part of the training.
Within two times 2-hour sessions, image analysis as well. Well, very briefly, you can touch on image analysis, I guess.
Yeah, it's enough to get people started, and then there's a bunch of really great tutorial videos that Dragonfly have put out, and I point people towards them. And people almost always come back for 10-20 minute sessions here and there to help with their analysis.
Yeah, and what is the typical data size?
So the 1000 to 1 voxel to field of view ratio images are around 1.6 gigabytes. If you do,
so not too bad. Still large, but not too bad. Yeah. Okay.
And then if you do the 2000 to 1, it's like 16 gigabytes. So then it starts getting a little trickier, a little slower.
Getting there.
And then for the image analysis, you need a really powerful working station, a lot of RAM. And we have those workstations available that you can remote into or at quite cheap rates.
Dragonfly is not easy to get started, right? Once you know some part, is it okay or still difficult?
Yeah, I think it's pretty, it's difficult. Yeah, definitely. There's a big learning curve. If you're already familiar with the world of image segmentation, all these things that exist in something like ImageJ or MATLAB or Python also exist in Dragonfly. So if you have that background, I think that would help a lot. So you're sort of learning two things. You're learning a software package, and you're also learning an entire new language around image segmentation.
Yeah. I watched a few Dragonfly presentations, but they do it so nicely, quickly, but many steps.
Yeah, and there's little details like, depending on what you're clicked on, certain menus will or won't be available. That's always a big problem for new users. Like, where did that button go? And it's just because you haven't selected the right thing somewhere else. And then, in your mind, you want to do something. I want to, like, let's say, sharpen this image, or I want to know the difference between, this toothpick and this fiber. And in your mind, you could imagine something that would work, but the real language to describe that and what how it's actually done is a whole other language. So that's the hard part. Working out what you can't do. Working out what you can't do really helps choose what you can do.
Okay. Yeah. Well, it's nice, non-destructive technique, right?
Yep.
Then I think science usually recommend you do this one first, then going into more detailed study in their spectrum of characterization. Okay, so